Good day, everyone. Welcome to this IPCOS webinar. Let me start by introducing IPCOS. After that, we'll try to answer the question, why do we do benefit studies? There are more answers to this question. Some may be very obvious and others may be less obvious. After that, we'll be looking at the methodology that IPCOS applies when doing a benefit study. We will go in depth and look at some of the methods of data analysis that we apply. We'll be taking a look at some of the examples of benefit studies that we have done in the past, and then we'll have a session of questions and answers. Okay, a quick introduction to IPCOS. We are a company that provides expert process control services. We combine in-depth process knowledge and operational experience with state-of-the-art process control. Our business is mainly a people business. The knowledge and experience of our people is what brings value to you, our customers. So that's why we always show a picture of our team, as you can see here. These are the people that will actually make a difference on your plant. We have 5 offices in Europe, the Middle East and India, but we are actually active all over the world, on every continent. Most of our activities, though, are centered on Europe and the Middle East. IPCOS is an independent services provider. We provide services to customers for any type of DCS and any type of advanced process control software. We do studies and audits. We do PID tuning, APC and training. For the APC activities, as I mentioned, we service any type of APC, including DMC+, SMOC, RMPCT, etc. We also provide our own APC software, which is called Inca APC. And for PID tuning, we have 2 excellent tuning tools. The one is Inca PID Tuner and the other Inca Aptitune. If you want to know more about these, please contact us or visit our website. We are very proud to show this slide with some of our respected customers. You'll probably recognize many of these names, but even more importantly, we are proud that 70% of our customers have been with us for more than 5 years. So hopefully that says that we are doing something right for them. Okay, the topic of this webinar is APC Benefit Studies, Value and Methodology. Let me just quickly introduce myself. I'm Leo Lategan. I'm APC consultant at IPCOS. I have been with the company for 6 years almost, and I have about 16 years of APC experience. Okay, let's start by answering that very valuable question. Why do we actually do benefit and feasibility studies? The obvious answer is that we want to assess the value that APC would bring to your plant. There are many quantifiable aspects related to this. For example, production increase, energy savings. There are also many not so easily quantifiable aspects, like the increased stability that you could get from APC, the reduction in operator intervention that you could get from APC. We also use this to do a detailed justification of the costs of a project. The typical payback period of an APC project is about 6 months. So that shows that the relationship of cost and benefit is very, very good and very much in your favor. The basis for APC implementation is also a very important aspect of such a benefit study. It is really an amount of pre-work of the actual project. During a benefit study, sorry about that, during a benefit study we will already determine the APC scope. We will look at APC strategies that we have to apply to actually achieve the benefits that we will propose. We may already define all the control handles that will be needed for the final APC application. Of course, we also use the benefit and feasibility study as a basis for any contractual benefit guarantees. This is something that we may do in certain cases really to guarantee the benefits and actually put part of the project revenue at our own risk. With a benefit study, we will also demonstrate to you as a client early on that APC can change the way that the plant is operated. This very often brings new ideas to light. That is a very valuable learning experience for the client. It is also an early exposure of the client to new technology. It's also the first opportunity of a very essential client-vendor teamwork. APC is very much teamwork. There has to be good operation between the consultant engineer and the on-site team. It is important also to assess APC readiness on your plant. We would look at instrumentation, we would look at the DCS and all its possibilities, we would look at the operator experience, and according to those findings we can tell you whether you are ready for APC or whether there are some changes that still have to be made before that will be the case. Doing a benefit study and using that as a precursor for an actual project is really a way of maximizing the chance of a very successful APC project. The methodology that IPCOS applies when doing a benefit study, let's look a bit more at that. We really try to maximize and streamline our time that we spend on site. Therefore, we distribute a questionnaire to the client before the site visit. Through this questionnaire, we ask questions like, who is the plant licensor, what equipment is used. That way, we can already at the early stage make use of our past experience on similar plants. We ask what the state of the instrumentation and of the DCS is. We try to get information about the typical operating constraints and the strategy for operating the plant. We usually also ask for some supporting documents like operator screen prints. Those are usually very valuable for learning the plant well at a very early stage. We ask for PFDs and PNIDs, tag lists, and very valuable, if it is available, historical data. Well, this way we try to be well prepared, come to site and streamline our activities on site very much. The actual site visit very much revolves around a number of interviews. The most important of these, I would say, is an interview with the operators in the control room. We would typically ask them to describe the plant for us from front to back. This gives us the opportunity to learn about all the ins and outs of the plant and to come in at different stages and drill down to the really important details like the operating strategy and the constraints and the limitations. We would also ask them to describe their normal site activities, their normal shift activities, and specific problems and issues that they have. With these questions we try to get to the surface which are the important indicators that the operators watch, what the targets they aim for, and what the product specifications are, for example, exactly where the constraints and limitations are in the plant. And this way we can assess which are the potential areas of optimization. Many operators also have some very good ideas about areas of optimization. We would usually ask them whether, for example, they try to maximize the feed themselves. What do they actually do to try to save energy? And what their views are on optimization and improving production. The next thing that is very important to us is the existence and the use of base layer advanced regulatory controls. How used are the operators to using these control loops, and how well do they actually function? Some of them may be used as a basis for APCs, some may be replaced by APC. So at this point in our study, it is very interesting to get answers on all these questions and see what the state of the base layer controls on the plant are. The next round of site interviews are usually with a plant or a production engineer, and this way we try to get a broader view on things. We would typically ask them about the strategy of operation. For example, do they give preference to feed maximization versus efficiency of the plant? How do they compare feed maximization to keeping the product quality, controlling that strictly? Think about a furnace, for example, where you could control certain constraints by dropping the severity or reducing the feed. We would talk about product qualities versus energy consumption. Very pure products can be obtained at the cost of using more energy. And we all know that at some point that efficiency is not increasing anymore. So it's a very nonlinear relationship. And these are valuable questions that we want the plant or the production engineer to answer for us. Also important information is to be able to determine the scope of the study. We need to focus on where the expected benefits actually are in the different units. For example, utilities. Would we include utilities or exclude it? If we can, if we have the possibility to save steam in a certain way, do we also need to include certain constraints on the steam network in our APC design? The plant engineer would typically tell us more about certain plant constraints and certain design values. In the case of ammonia, for example, the steam to carbon ratio, the air to gas ratio, and in the synthesis loop, the hydrogen to nitrogen ratio. In the case of an ethylene plant, we could think about the feed rate versus the severity on the cracking furnaces. In the case of refining, we could think about the different crude types and different modes of operation that could be applied, like naphtha maximization mode compared to kerosene maximization mode. So really the interviews with the plant engineers is on a bit of a different level than what we would do with the operators. In many cases, I would say, we have senior operators which could fulfill this role. And in other cases, we have our interviews with a mixed group that can all make use of their specific expertise to answer our questions. Lastly, the managers, we need to talk to them about non-technical information, which is also very important. In this group, I could maybe also include the planning department. We need to get their views on the strategy and their long-term goals. For example, if we are actually able to increase production by 1%, can this be sold on the market? Can it always be sold on the market, or is it a seasonal phenomenon? Can it be processed downstream? If we are able to increase the throughput by 1%, will the raw material always be readily available to be able to do that? Lastly, we shift our focus to DCS and control engineers. As I said already, it's very important to have knowledge about the current base layer, advanced regulatory system, and also DCS. This is very important to ascertain whether the plant is ready for APC and whether we would need to implement or make major changes to the base layer. The procedures for DCS modifications is also very important. We need to know, for example, if we implement DCS modifications, can those only be downloaded to the live system during plant shutdown, or can it be done at all times? Would it require lengthy MOC procedures for these base layer modifications? All of this could influence when we can actually start with an APC project, whether it is at all possible without going through a round of basic control modifications first, and of course the possible schedule of such an APC project. Over and above interviews on site, it is very essential for us to have high quality data to be able to do a detailed and a good benefits estimate. We need data that is not overly compressed. Typically we would say 1 hour sample data is good enough, and then typically we would ask for 1 year of data so that we can cover different seasonal constraints, different operating modes, etc. We would usually require process data and also LIMS data, that is laboratory data, and we would do some statistical analysis on some of the key variables. We would typically look at the reduction in the standard deviation of certain key variables. We would also rely on actual experience of IPCOS. We would rely on literature. We would rely on published case studies. That is really to determine how much we would be able with APC to reduce the standard deviation on these key variables. It is generally accepted that APC can bring a 50% reduction in standard deviation. But if we see from past experience that more is possible or less, then we would go with those targets. Because of this reduction in standard deviation, we are able generally to operate much closer to the actual limit. We can actually shift the average closer to limit without increasing the number of transgressions across this limit. And that change that you would see, that is the benefit. Here's a graph to actually explain that in a bit more detail. You can see where APC comes into play. The standard deviation is reduced. That enables us to operate much closer to the constraints while having, for this graph, the same number of transgressions as before. Of course, once we have identified the key variables where we would be able to reduce the standard deviation and push closer to the limits, we need to translate that into some kind of real benefit. And for that, we typically need process models. This would help us to quantify the actual benefit in terms of production increase or energy savings. These process models can typically be obtained from either historical data. We could even make steps on the plant during our site visit to get some plant responses that we need. If available, we can use a process simulation. We can also use general process knowledge. For example, if it is well known that an X increase in temperature gives a Y increase of conversion, and accepted in general, that is information that we can use as a process model. We can also use some calculations. For example, we can look at mass or energy balances around certain units on the plant, or we can look at reaction stoichiometry. Let me show one example which could clarify some of these things we have talked about. Let's take an ethylene plant where we are able to maximize the feed typically. Most benefits are locked up in feed maximization on an ethylene plant. In this particular case, the throughput limiting constraint was a crack gas compressor. By looking at some historical data, where we had major increases and reductions in feed, we were able to obtain a process model of the total plant feed against the suction pressure of the crack gas compressor. Taking this key variable and assuming that we would be able to reduce the standard deviation by half, we were in this way able to move much closer to the limit, while keeping the same number of transgressions above this limit, and that way we were able to increase the total feed to the plant. This here is the actual process model using our normal model identification tools that we could get. This basically shows if you would increase the total feed by 1 ton per hour, what change would you see in the suction pressure of the crack gas compressor. And this was very valuable for calculating at least one part of the benefits that we could estimate on this ethylene plant. So what we see here is analysis of this data. It is a distribution plot in red of the actual data, the actual suction pressure of the crack gas compressor. You can see the minimum value that we had in this data set, which stretched over a few months, was 0.51 bar, and the maximum 0.6. The blue line there is the mean. The blue is a normal distribution with the same characteristics as the actual data. And the brown is the normal distribution. And then the blue is a normal distribution which shows what it would look like if we would actually halve the standard deviation. The green line there is the actual high limit of the crack gas compressor pressure. The next plot shows what benefit this holds for us. In this case, I showed the superimposed normal distribution, the one in brown, and the blue line where the standard deviation was halved as a cumulative plot, because that shows us much better at the end what the actual benefit could be. The point of this plot is really that above the limits, that is everything to the right of the green line, the area under these plots are actually the same. So we don't have an increase in transgressions across this limit. But because of this reduction in standard deviation, we are able to push the mean value of the distribution much closer to the limit. And this difference in the suction pressure, that is the difference between the yellow vertical line and the blue vertical line, that is the benefit that we are talking about and that we had to relate again to actual increase in the throughput of the plant. A second example, we could typically think about the furnace draft control. That could apply to any furnace, I would say. In this case, or cases where we often work on, it would be the primary reformer on a methanol or an ammonia plant. In this case, it could be beneficial to reduce the standard deviation in the excess oxygen in the stack of the furnace. This means we would be able to move much closer to the low limit of the oxygen, and we could allow APC then to reduce the excess air that is pumped into this furnace and that has to be heated as well. Using a very simple mass balance calculation, Okay, we are able to calculate the reduction in fuel gas by halving the O2 measurement, the standard deviation of the O2 measurement in the stack. That is a lot of energy savings, and in the case of ammonia or methanol, every kilogram of fuel gas that we save is available as a throughput to the plant. So there are some added benefits to that as well. A third example could be just a simple distillation column control. For example, methanol distillation, which we have a little graph to prove how we would go about to calculate the benefits from. You can imagine that if we are able to tightly control the top quality of this distillation column, we are once again able to move the average much closer to the actual production specification. This could typically represent a reduction in the reflux of the column, and this in its turn may represent a reduction in the reboiler duty, which if it is using steam, for example, it would be a huge saving in energy. In this case, we had to estimate the process model, that is from the top quality to the actual steam saving from historical data. We had to look back in our historical data, and we eventually found a past occurrence where a change happened in the plant and a change in top quality, the impurity in the top in this case, coincided with the reduction in the reboiler steam. In this plot in blue you can see the steam flow to the reboiler of this methanol distillation column, and in red there you can see the increase in the ethanol impurity in the top quality. So this data here helps us to actually find a process model between the shift in the average of the top quality and in its relation to the steam saving on this column. After having played around with data for a certain time, we would typically write a report to the customer. The level of detail in this report would typically depend on the price paid for the study. It would also, it will always, in all cases, actually be a good basis for looking at the commercial viability of a project, and as I've explained before, also the technical feasibility of such a project. I would say the most detailed variation of a report will include accurately quantified benefits, which would be able to, from which we will be able to calculate the costs that an APC project will need, and also the benefits to the customer. We will typically describe all the strategies to achieve this, which would be in different places in the plant, and also the non-quantifiable benefits, for example, increasing plant stability and reduction in operating intervention. These things are not necessarily quantifiable, but they are very valuable in the end to production. Typically, we would then include a preliminary APC functional design, which is already some pre-work of the actual project. It is very interesting sometimes to do a comparison of the benefit estimates to a post-audit comparison, which is very often part and parcel of an APC project. Of course, this is very important to do also where we have included a benefits guarantee in our contract. IPCOS typically does conservative benefit estimates. This relies not only on the data from a particular study, but also on collective experience from similar studies that we have done in the past. Because not all studies will result in a project for IPCOS. In some cases we may point to some optimization or instrumentation issues that have to be fixed first, or equipment issues. In general, we can say that the post-audit results that we find usually compare well to the estimates we have done before. Ideally, we would expect the benefits achieved to actually exceed those that we predicted. Of course, naturally, because we guarantee benefits, this would be a very valid expectation from our side. Here is one example of a comparison of the post-audit benefits to what we predicted before. In this case, the benefits actually achieved was about 50% more than what we estimated before. The distribution was a bit different. For example, this is a methanol plant. We could say that the reformers section in the end achieved much more than we actually predicted. Some of these changes or some of these differences are in some cases because of equipment problems or instrumentation problems. Some parts of the plant did not end up being the scope of the APC, and in some cases the post-audit calculations were done in a more global way. So some of the predicted benefits were rolled up into a different category. But in general, we could say that this is really a good comparison of what was actually achieved with what we estimated before the time. Our conclusions: a benefit study is a very valuable first contact between IPCOS and its client. Typically, the client may learn a lot about their plants. Sometimes, due to our work, they could consider different ways of operating the plant. Also because we have a data-based approach, very often the site activities, the daily life on site is too busy. It does not really allow for much investigation into the data. And our approach is really data-based, and we can prove with data being king that certain benefits can be achieved and that different ways of operating the plant could be beneficial. We can say that the benefit study can very easily evolve into the functional design phase of an APC project. Some of the work has already been done. For example, during the benefit study, we would already define the APC scope and many of the strategies that would be applied. Even some of the control handles will already be defined before the time. Okay, this brings us to a session for questions and answers. If you could use the Q&A window on your WebEx screen for that. We'll try to get some answers on your most pressing questions. Please go ahead. Okay, the first question: what is the difference in the work, the analysis, or the approach between a study where you give benefit guarantees and where you do not give benefit guarantees? I would say in principle there is not much of a difference. Benefit studies can be done to varying degrees of detail. This is also influenced by the availability and the quality of the data, and naturally by the price paid for the study. To be able to give good benefit guarantees, we would prefer more detailed data analysis. But in some processes, we can also very strongly rely on some past experience, like, for example, ammonia or methanol. Second question: can you make a distinction between the benefits from optimizing the PID base layer and the APC part. I would say the benefits for only the PID or the base layer optimization is difficult to quantify separately. Typically, we would roll it into one. Naturally, the PID base layer optimization is a very important prerequisite for a successful APC implementation. Does a benefit study lead to savings in the implementation cost of an APC project? Most definitely yes. Many activities undertaken for a benefit study has to be done anyway at the beginning of the functional design or the pre-step test phase of an APC project. The benefit of having a separate benefit study is that there is this point in between where you are able to make a decision of going ahead with the project or not. Okay, this is an interesting one. Can some of the benefits suggested in your analysis not be achieved just by operators running the plant in a different way? I would lie if I say that is not the case, because indeed a benefit analysis may bring new ideas for optimization to the surface. That is why it can also be a very valuable study to the client, also as a standalone. Operations may start thinking about running the plant in a different way to achieve some of these suggested benefits. But still, I would say the exact value of a constraint pushing APC application, which is running and observing the limits of the plant every minute and using its multivariable model predictive capabilities, would never really be achieved by the operator, simply because he cannot do this every minute, and he will always tend to stay a safe distance away from the actual plant constraints. Okay, we'll make this the last question. Can you take into account the benefits that will be created if some valves will be repaired in the near future? Of course, this will very much depend on specific valves or instrumentation we are talking about, but in general I can say that we take a holistic approach when looking at calculating benefits. Benefits will be based on pushing against the real constraints. If the valves under question forms an important part of the proposed APC strategy, then it will be suggested to repair them before APC is feasible. But I would say I believe in most cases we can still predict the benefits even before certain instrumentation or valves have been fixed. Okay. Another question, why look at data if you use a model? Well, I would say we need to develop a base case from history data, and then we always need to validate the model. That would be like simulation model against the real data. So data is always very important to us. Okay. Would we typically use hourly averages of data or just raw data? I would say if we look at, if we have data on an hourly basis, we would typically look at the average. Naturally, if it is viable to get data at a higher frequency, that is always better and more valuable. But we would say that a least requirement is hourly averages of data. If there are any more questions or questions that come up later, please feel free to put them in email and send them to us. The email address to send them will be shown shortly. So we'll end this Q&A session now. Thank you very much for your participation. There you could see the email address to which you can post any more questions, or even if you'd like a copy of today's presentation. There's a link to our website, and eventually this presentation will be posted on YouTube. You can just go to YouTube and search there for IPCOS. Our next webinar that will take place on the 14th of June, 11:30 Central European Time. The topic would be PID optimization with aptitude on a hydrocracker unit. PID tuning is often based on simplified models and assumptions. For any situation that deviates from that simplified model, this will fail. A typical example is when instrumentation issues, for example, introduce additional complexity. In this case, study on the PID tuning of the hydrocracker quench valves, we will demonstrate how this feature-based tuning of our aptitude package can assist the control engineer in tuning the highly interactive process when faced with the degraded performance of these control valves. So, sounds very interesting to me, and I hope you can join us again in June. Thank you very much for your time.